I want to give you an overview of a large-scale quantum computer. Imagine you want to run a useful quantum computation, so something that you cannot do on a classical computer. How would you do it? Well, first you need a circuit for your computation, so maybe you ask an algorithms person and they give you a circuit like this. 100 qubits are enough to already run, for instance, classically intractable quantum simulations, but these classically intractable computations tend to be very long, possibly taking several hours or even days. So how do you construct a quantum computer that can run such a long computation? Well, the first step is to take a bunch of physical ingredients like superconductors, semiconductors, and put them together to a big quantum computing chip. Here's a small section of a big superconducting qubit chip. Well, not really, it's just two pictures of IBM's 16 qubit chip next to each other. But let's imagine it is a big quantum computer. With your 100 qubit computation in mind, you probably don't want to be worrying too much about semiconductors and superconductors, so you tend to make an approximation. You think of your physical components as two-level systems, as qubits. And that's not entirely accurate, but it helps you think about systems of hundreds of qubits. Now, 100 qubits are, of course, not enough to run our 100 qubit computation because these are faulty physical qubits. They tend to break after perhaps a few hundred microseconds. So you take many of those and combine them to logical qubits that actually survive to the very end of your computation. And you need hundreds of those to run your 100 qubit quantum computation. So potentially hundreds of thousands of physical qubits. And at that point, you certainly don't want to be worrying about semiconductors and superconductors, but you don't really want to be thinking about physical qubits and stabilizer measurements either. To construct a large-scale quantum computer, you'd like to have a framework that captures the essence of logical qubits and logical operations using only simple concepts, just like physical qubits capture the essence of your physical components using two-level systems. This talk is about such a framework, and the way I draw these things, it already looks a bit like a board game. And this is the way I would like to introduce to you this framework, as a board game where the board corresponds to your array of physical qubits, and the pieces that you can place on the board are logical qubits, surface code patches. The goal will be to use the rules of the game to implement our 100 qubit computation. The game is played on a board partitioned into a number of tiles. Each tile corresponds to d squared physical qubits, where d is the code distance. Here it's 5, but typically it's a number between 10 and 30, depending on how much error correction you actually need. The pieces that you can place on the board are patches. Patches represent qubits, and there are two kinds of patches. There are 4-corner patches and 6-corner patches. 4-corner patches have 4 corners and 4 edges, 2 dashed edges and 2 solid edges. The dashed edges of each dashed edge of a qubit represents the qubit's Pauli X operator, and each solid edge represents the qubit's Pauli Z operator. With surface codes, patches correspond to surface code patches, with dashed and solid edges corresponding to rough and smooth boundaries. By the way, I realize QIP has a very broad audience, so not everyone may be super familiar with surface code. So if you don't understand everything that will be going on the right-hand side, don't worry about it too much. The left-hand side is the important one. These patches come in different shapes and sizes. So for instance, this rectangular one in the bottom left corner, or the one in the top right corner where you have a dashed and where you have an X and Z edge on the same side of the patch. I won't be drawing these Pauli labels anymore. Just know that dashed edges are X operators, solid edges are Z operators. And then there are these 6-corner patches. They occupy 2 tiles and represent 2 qubits, with the first qubit's Pauli X and Z operator in these top 2 edges, and the second qubit's X and Z operator in the bottom 2 edges. With surface codes, it's just a patch with 3 rough and 3 smooth boundaries. These 6-corner patches won't be too important. We'll just use them in one specific context later on. So that's the board and the pieces that you can put on the board, but what are the actual rules of the game? Well, there's a certain set of actions that you can perform. Some actions have a time cost associated with them, while others don't. So there's this little clock here counting the time steps. The idea is that one time step roughly corresponds to d code cycles, so measuring all stabilizers d times. We'll associate a time step with all operations that with surface codes have a time cost that scales with the code distance d, and no time step with operations that don't scale with the code distance. So that's why it's only roughly equivalent to d code cycles. The first set of operations is initialization. It's how you put patches on the board. You can initialize patches in the 0 state or in the plus state, or you can initialize 6-corner patches in 0, 0 or plus plus. And because with surface codes, this corresponds to initializing all physical qubits in the corresponding state, which doesn't scale with the code distance, this doesn't have a time cost associated with it. You can also initialize patches in states that are not Pauli eigenstates. For instance, one state we'll be interested in is this magic state, 0 plus e to the I pi over 4, 1. But when you do this, there's a certain probability that an error will occur. So for concreteness, let's just say that with a probability of 10 to the minus 4, we'll initialize one of these 3 states instead. There will be a Pauli error, and we will not know when this happens. With surface codes, this corresponds to state injection. There are many protocols for state injection. For instance, this one by Andrew Landau and Kieran Ryan Anderson, where you start with a magic state, a physical magic state in the middle, and a stabilizer state around it. And then you just switch the stabilizer configuration to your surface code patch and measure these stabilizers for 3 code cycles. State injection isn't fault tolerant, so the time to do it doesn't scale with the code distance. That's why we don't associate a time step with it. There are also other protocols, for instance, the one by Ying Li. Now, measurements. You can measure patches in the X or Z basis. This is also the only way to remove patches from the board. For instance, if we measure this 0-qubit patch in the Z basis, the outcome of the measurement will be +1, and the patch will be gone. We can also measure these patches in the Z and X basis. The measurements will have some outcome, and the patches will be gone. With surface codes, it corresponds to measuring all physical qubits in the corresponding basis, so again, doesn't scale with the code distance, no time cost. The interesting operations are the next 2 ones. If you have 2 patches in neighboring tiles, then you can measure the product of the 2 Pauli operators that are next to each other using a 2-patch measurement. So for instance, in this case, we have 2 patches next to each other, and their 2 Z operators are next to each other. So we can use a 2-patch measurement to measure the operator Z times Z. With surface codes, this corresponds to lattice surgery. So you change the stabilizer configuration to this one, and you measure these stabilizers for D code cycles to account for measurement errors. The outcome of the ZZ measurement will be the product of these red stabilizers. And then you split it again. So these kind of Pauli product measurements are a way to generate entanglement between qubits. What happens in this specific example is we start in the state 0, 0 plus 0, 1 plus 1, 0 plus 1, 1. If the outcome of the ZZ measurement is +1, we end up in the state 0, 0 plus 1, 1. If the outcome is -1, we project into 0, 1 plus 1, 0, and both are entangled Bell states. You can also measure other Pauli product operators with that. For instance, in this case, we have 2 patches, and one patch's Z operator is next to the other patch's X operator. So a 2-patch measurement can be used to measure X times Z. Again, it's lattice surgery, just the stabilizer configuration looks a bit different. You can even measure operators that involve the Y operator. For instance, in this case, you have 2 patches next to each other, and the Z operator of one patch, it is adjacent to both the X and the Z operator of the other patch. And because Y is X times Z, you can use a 2-patch measurement here to measure Y times Z between these 2 qubits. Again, it's lattice surgery, but the stabilizer configuration includes this weird 5-qubit twist effect. What's even more interesting is that you can measure products of more than just 2 Pauli operators. In fact, any number of Pauli operators using a multi-patch measurement. The way it works is the following. You can initialize an ancilla patch that only survives for 1 time step. But during this time step, you can measure the product of any number of Pauli operators next to the patch. So for instance, we could use this one here to measure Y1 times X3 times Z4 times X5 of 4 qubits. And after the measurement, this ancilla patch is gone. The fact that this is possible with surface codes was, to my knowledge, first pointed out by Austin Fowler and Craig Gidney not too long ago. The way it works is basically the following. In this ancilla region, you initialize all physical qubits in the plus state, and then you measure these stabilizers here for D code cycles. The product of all the stabilizers with a red dot will be the outcome of your measurement. It's basically multiple lattice surgeries at the same time. The final 2 operations are rather simple. You can change the shape of your patch by moving its edges or corners. If you move the edge of a patch and the patch becomes larger in the process, then this costs 1 time step because it involves measuring new stabilizers for D code cycles. If the patch becomes smaller, then it costs 0 time steps because then it corresponds to just measuring a bunch of physical qubits. You can also move edges around corners like this, for instance. And you can even move corners of patches. So for instance, we can move this top right corner to the top left. This means changing the stabilizer configuration, measuring this for D code cycles, so it costs 1 time step. Okay, so these are the rules of the game. You can put patches on the board by initializing them in 0 plus or a faulty magic state. You can remove them by measuring them in X or Z. You can measure Pauli products through 2-patch and multi-patch measurements, and you can change the shape of patches. Our goal now is to use these operations to implement our 100-qubit quantum circuit. A popular gate set for these circuits is Clifford plus T, but I like to express my circuits in terms of Pauli product rotations, so operations that are e to the minus I p phi, where p is a Pauli product operator and phi is a rotation angle. In this sense, the S gate, the phase gate, is a Z pi over 4 rotation. The Hadamard gate is a product of 3 rotations, Z pi over 4 times X pi over 4 times Z pi over 4. The C0 gate, just like the previous 2 gates, is a Clifford gate, so it can also be expressed in terms of pi over 4 rotations, but it's a 2-qubit gate. So it involves this 2-qubit rotation, which is this Zx rotation. So the Pauli operator of the rotation is Z times X. And then there are 2 single qubit rotations, Z minus pi over 4 and X minus pi over 4. And the T gate is a Z pi over 8 rotation. So a generic 4-qubit circuit could look something like this. You have a bunch of pi over 4 rotations in orange, you have a bunch of pi over 8 rotations in green, and you have a bunch of measurements in the end. Measurements are blue boxes, where the operator in the box tells you the basis of the measurement. The first thing I like to do is commute all my Clifford gates, all the orange boxes, to the end of the circuit. And the reason why you can do this is because Clifford gates map Paulis onto other Paulis. So if you want to move a Clifford gate past another rotation, you just have to check whether the 2 Pauli operators commute or not. If they don't, you multiply them together and change the basis of the rotation. So for instance, this X pi over 4 rotation, if I want to move it past the Z pi over 8, then I can do that, but it changes the Z pi over 8 rotation to a Y pi over 8 rotation. I can use the same trick to absorb Clifford gates into measurements, changing the measurement basis in just the same way. So for instance, these X pi over 4 rotations in the very end, if I absorb them into the measurements, they become, the Z measurements become Y measurements. Commuting Clifford gates in this way can also turn Pauli operators into Pauli product operators. So for instance, if I commute this X11Z pi over 4 rotation past the Z pi over 8 rotation, it will turn it into a Y11Z pi over 8 rotation, so multi-qubit rotation. And it will also turn Pauli measurements into Pauli product measurements. So I can continue commuting all my Clifford gates like this to the very end of the circuit until I end up with something like this that only involves pi over 8 rotations and measurements. So any circuit can in principle be written as a series of pi over 8 rotations. So let's say we do this to our 100 qubit circuit, we commute all the Clifford gates to the end, and we find that it's a series of 10 to the 8 pi over 8 rotations. 100 qubits and 10 to the 8 T-gates, that's what, for instance, Babush and co-authors found for classically intractable Hubbard model simulations. So now we have to perform all these rotations, but I only showed you how to do measurements. And that's, of course, where magic states enter. So if you want to perform a p pi over 8 rotation and you have a magic state available, what you can do is you can measure the Pauli product p times z between the qubits and the magic state. And depending on the outcome of this measurement, there might be a Clifford correction. But that's just a pi over 4 rotation that you can, again, commute to the end of the circuit. So it's nothing to worry about. With that in mind, so since we can only initialize faulty magic states in our framework, but we need good magic states to go through our 10 to the 8 pi over 8 rotations without any errors, we'll need magic state distillation. With that in mind, an intuitive way to design your full quantum computer is to partition it into a block of tiles that you use to generate magic states, a distillation block, and a block of tiles that stores the 100 data qubits of our computation and consumes magic states to advance the computation. This data block in blue, and the distillation block is orange. So here's an example of a 4-qubit quantum computer. If let's for now treat magic state distillation as a black box that just outputs magic states every, say, 5 time steps. If the first operation that we need to perform in our computation is this x1yz pi over 8 rotation, then what we'd have to do is, well, we wait for 5 time steps for a magic state to appear. Here it is. And now we consume it by measuring x1yz times z using a multi-patch measurement. And then we repeat this process for the next rotation. So this is a quantum computer that executes 1 pi over 8 rotation every 5 time steps until you reach the end of your computation. And you execute 1 rotation after the other. What I want to do now is show you a few designs for data blocks and distillation blocks, starting with data blocks. So in principle, the thing shown here can be used as a data block, but it's a bit wasteful with tiles. It uses 4 tiles to store each qubit. You can do much better than that. For instance, with this thing, where you use roughly half as many tiles, namely to store in qubits, you use 2n plus square root of 8n plus 1 tile. And it does that by using 6-corner patches. Remember, 6-corner patches are these patches that represent 2 qubits, with the first qubit's Pauli x and z operator in the left 2 edges, and the second qubit's Pauli x and z operator in the right 2 edges. So if there's a magic state generated in some adjacent distillation block, it can be consumed through a multi-patch measurement like I showed you previously. And any Pauli product operator can be measured that way. For instance, this one, which involves the Y operator of the first qubit, the X operator of the second qubit, the Z operator of the 11th qubit, and so on. If you want to build smaller quantum computers, you might want to use smaller data blocks. For instance, this one, which only uses roughly 1.5 tiles for each qubit, or to be more precise, it stores n qubits using 1.5 n plus 3 tiles. And it stores these qubits in square patches. Now the problem with that is that in this setup, only the Z operator of each patch is accessible by multi-patch measurements. The X operators and Y operators by extension are all kind of buried in between patches. And we'll have to do something about that. And it will turn out that this means that in the worst case, the consumption of a magic state can take up to 9 time steps. Let me show you why that is. Here's a 6-qubit example. The blue region is our 6-qubit data block, and the orange region is our distillation block that we still treat as a black box. The first operation that we need to perform is this Z11ZZZ Pyruvate rotation. Well, here we got lucky. That's just something that we can do right away. We just consume the magic state by measuring ZZZZ times Z. Then we measure the magic state in X. It's gone. Okay, the next rotation involves X operators. To measure these, we'll need to rotate some of the patches, namely patches 2, 3, 4, and 5. If you have a driver's license, then you know how to do this. You just need to implement a 3-point turn using using patch deformation. So we move these edges down here. It takes 1 time step. Then we move this corner down here. It takes another time step. Then we move this edge down here. This takes 0 time step because the patch became smaller. Then we move it back up again a time step, and we move the other edge back up. So altogether, this takes 3 time steps to rotate a patch. We repeat the same thing for patch number 4. Like this. And now we can consume the magic state by measuring X times X times X times X times Z times Z. So this took us 7 time steps, but the worst case is a rotation that involves Y operators, because there's basically no way we can ever measure Y operators with this thing. There's just not enough space. The way to get around this is basically to insert a resolution of the identity into the circuit. You have a pi/4 rotation followed by a minus pi/4 rotation. And you choose these pi/4 rotations in a way that if you commute them past the pi/8 rotation, all the y's turns into x's or z's. But now you have these pi/4 rotations that you actually need to perform explicitly. Naively, you would think that this requires a y eigenstate, which we cannot actually initialize, but you can also just use a z eigenstate instead and a y measurement. So what this circuit right here tells you to do, if you want to perform a p/8 rotation, you initialize a qubit in the 0 state, and you measure p times y. So for this z/4 rotation, you measure z times y. And then you measure the 0 qubit and the x basis. Then you repeat the same process for the other pi/4 rotation, measuring x1, xz times y, and you remove the thing by measuring it in x. So now you're left with a pi/8 rotation that only involves x's and z's. Well, this one we know how to do. We rotate a bunch of patches in the top row, we rotate a bunch of patches in the bottom row, and now we can consume the magic state. So that's the worst case scenario. That's why it takes up to 9 time steps to consume a magic state with these things. Okay, so those were the 2 data blocks that I wanted to show you. Now let's turn to magic state distillation. Magic state distillation is this short computation that you'll be repeating over and over and over and over again, so it's really worth optimizing it. If you've ever seen a distillation circuit in your life, then it's probably this one for 15-to-1 distillation, which is based on a 15-qubit quantum error correcting code with a transversal T-gate. So meaning that the logical T-gate of the code corresponds to a T-gate on each qubit. It works like this. You start with 10 qubits initialized in the 0 state, 1 qubit for each of the 10 Z stabilizers of the code, 4 qubits initialized in plus, 1 for each of the 4 X stabilizers of the code, and 1 qubit in the plus state for the 1 logical X operator of the code. The first set of operations is a bunch of C-naughts. That's the encoding circuit of the code. C-naughts map Z's onto products of Z's and X's onto products of X's. These C-naughts are chosen in a way that they map the Z operators of the bottom 10 qubits onto the 10 Z stabilizers of the code, the X stabilizers of the first 4 qubits onto the 4 X stabilizers of the code, and the X operator of the 5th qubit onto the X logical operator. So after these C-naughts, you end up in a state where you know that all Z stabilizers are +1, all X stabilizers are +1, and the X logical operator is +1. So it's a logical plus state. Next, you perform a logical T-gate, turning the logical plus state into a logical magic state. And you do this transversely, so by performing these 15 T-gates. But they're faulty T-gates. You perform them using faulty magic states. But because this is an error-correcting code, we can actually detect errors by measuring the stabilizers of the code. So we go through the encoding circuit backwards and measure these qubits here, basically measuring the stabilizers of the code. If any of these measurement outcomes is -1, then we've detected an error, and we throw everything away and we start again. But if the outcome of all of these measurements is +1, we've distilled a magic state, with an output error rate of 35p to the third in this case, compared to the input error rate of p. Okay, let's manipulate this circuit a bit. The first thing we can do is we can move all these C0s to the end of the circuit, turning the Z Pyruvate rotations into Z product Pyruvate rotations. These C0s, they nicely cancel, so we're just left with these rotations. Now let's take a look at the bottom 10 qubits. You start in a Z eigenstate, 0, then these qubits are affected by a Z rotation, which does nothing to them, and then you measure them in the Z basis, trivially yielding +1. So these bottom 10 qubits, they're completely useless. They don't do anything. We can just throw them away by cutting the circuit after the 5th qubit. And finally, we can absorb these first 4 Z Pyruvate rotations into the initial plus states, turning them into initial faulty magic states. So that's 15-to-1 distillation. Now let's implement this using 11 tiles, so just these 11 orange tiles here, not the gray ones. We start by initializing 4 or 5 qubits, 4 faulty magic states and a plus state. And now you'd think to go through the circuit, we could just use, so these are 5 qubits. Now, to go through the circuit, you'd think we could just use the circuit identity I showed you before to consume magic states to go through the circuit. But the problem with that is, with a 50% probability, these will generate a Clifford correction, turning the Pyruvate rotation into a Pyruvate rotation. In principle, this is something we can commute to the end of the circuit, but once they hit the measurements, they turn these Pauli measurements into Pauli product measurements, which take longer. And we want to avoid that. To avoid that, you can use an auto-corrected Pyruvate rotation, so basically a rotation that automatically applies a Clifford correction when you need it. It's based on the observation that in this Pyruvate rotation circuit, depending on whether you measure the 0 qubit in the X or Z basis in the end, you either perform a Pyruvate rotation or you perform no operation at all. Anyway, you can use this to construct the circuit here. What the circuit tells you to do, if you want to perform a Pyruvate rotation, you initialize a magic state and a 0 state, and then you measure P times Z, so in this case, Z times Z times Z times Z, and at the same time, you measure Z times Y between the magic state and the 0 state. Depending on the outcome of the PZ measurement, you measure the 0 state either in the X basis or in the Z basis, basically either performing a correction or not. And this you repeat for all of these 11 Pyruvate rotations until you get to the end of the circuit, where you also measure qubits 1, 2, 3, and 4 in the X basis. If all the measurement outcomes are +1, you've distilled a magic state using 11 tiles and 11 time steps. Or in other words, using 11 d² physical data qubits and 11 d plus subleading terms code cycles. By the way, if you're worried about these subleading terms, you can also use a few more tiles to make sure that it's exactly 11 d code cycles, but this may not be worth doing. Now a few things for the magic state distillation enthusiasts among you. These distillation circuits are extremely easy to obtain if you're familiar with the triorthogonal matrix approach by Bravi and Ha, where you take this triorthogonal matrix that fulfills these conditions, you put it in row echelon form by Gaussian elimination, you remove a bunch of columns, and you obtain this matrix that describes a code with a transversal T-gate, where each column of the matrix describes a physical qubit, and each row is either an X stabilizer or an X logical operator. Perhaps you can see already that it's very easy to translate it into a circuit. You just put a plus state for each row of the matrix, and then you just turn each column of the matrix into a Pyruvate rotation, reading off the Pyruvate rotation just by turning 1s into Zs and 0s into 1s. And in the end, you measure all rows that correspond to stabilizers in the X basis, and the other rows are your output magic states. So this one in particular, that's just 15-to-1 that we had before. But using this approach, you can generate all sorts of protocols, like 14-to-2 or 20-to-4, and the circuits all look very similar, and so do the implementations. In fact, there are infinitely many protocols that you can come up with. Sure, not all of them will distill magic states that are good enough, but out of those that do, how do you decide which protocol to use? What people usually do when they look at N to K distillation protocols, so protocols that distill K magic states from N bad ones, is they try to optimize the input to output ratio, so this N divided by K thing. But what you should actually try to optimize is the space-time cost per magic state. So, well, for the implementations that I showed you before, it turns out to be this thing here, which is not at all N divided by K. In fact, you can even come up with protocols where the N over K is 30 times better, but still the cost per magic state is significantly higher. So my point here is try to come up with better cost metrics for magic state distillation. All right, enough about distillation. With our data blocks and distillation blocks, we have all the components that we need to now construct our large-scale quantum computer and to go through our 100 qubit 10 to the 8 T-gate quantum circuit. To get actual numbers out of the resource overhead, let's assume that the physical error rate of our device is 10 to the minus 4, assuming circuit level noise. The raw magic state error rate is also 10 to the minus 4. We'll assume that one code cycle takes 1 microsecond, and that each tile corresponds to 2d squared physical qubits, also taking measurement and Silas into account. Our goal will be to go through the computation in a way that the probability of anything going wrong stays below 1%. Let me show you what I mean by that. Well, the smallest setup that we can come up with using the components that we have so far is this one, where we have this compact data block that stores 100 qubits using 153 tiles and can consume 1 magic state every 9 time steps. And this tiny thing over here, that's our distillation block that occupies 11 tiles and produces 1 magic state every 11 time steps. We should check that the output fidelity is good, that the output magic states are good enough to execute 10 to the 8 T-gates with the probability of any one of them failing staying below 1%. And 10 to the minus 11 is certainly good enough for that. So in total, this is a 164 tile quantum computer that executes 1 T-gate every 11 time steps. So it takes 11 times 10 to the 8 time steps to go through the computation. To find out how many qubits and code cycles this corresponds to, we'll need to know what the code distance is. And to do that, you can use this approximation, for instance, for the logical error rate of a service code patch under a circuit level noise. And we'll need 164 of these patches to survive for 11 times 10 to the 8d code cycle. So this entire quantity over here should stay below 1%. And we find that distance 13 is good enough. So this entire thing is a 55,500 physical qubit quantum computer that finishes the computation in roughly 4 hours. If you want to speed up your computation, what you could do is just add another distillation block. Basically, now you'll be producing magic states twice as fast, 1 every 5.5 time steps. But our data block cannot keep up with that because it can only consume them 1 every 9 time steps. So this will be our bottleneck. Still, we increase our qubit count only by a bit, but our computational time drops significantly by 45 minutes. If you want to speed up beyond that, you should use the data block, the other data block that we have, the one where you store 100 qubits using 231 tiles, which can consume 1 magic state in every time step. And the rest of your quantum computer would be 11 distillation blocks that altogether produce 1 magic state in every time step. So this is a quantum computer that can consume or perform a Pyruvate rotation every time step, or it uses 123,000 physical qubits, so only roughly twice as many as our smallest example. But the computational time drops significantly from 4 hours down to 22 minutes. So it was a good space-time trade-off. Unfortunately, we're almost out of time. This was just a small taste of what's possible with surface codes and lattice surgery. But there are many more things you can think about. For instance, you could try to think about ways to parallelize your computation by executing multiple T-gates at the same time, basically constructing bigger and bigger quantum computer that finish the computation faster and faster. And you can do this until you reach a limit that is set by the T depth. So if the T depth in our example were 10 to the 6, this limit would be reached with 386 million qubits. But the computation would be finished in 1 second. If you feel like that's too many qubits for a quantum computer, you can also think about schemes for distributed quantum computing, where you do the same thing using 1,500 computers with 250,000 qubits each. So still a lot of qubits, but distributed over multiple processors. You can also think about using resources other than T-gate magic states to speed up your computation, like CCZ states or small angle rotation states. If those are things that you find interesting, you can read more about this and other things in A Game of Surface Codes, Large-Scale Quantum Computing with Lattice Surgery. In case you find this title difficult to remember, here's a picture to help you out. I hope you enjoyed the talk. Let's take questions.
Thank you, Daniel. We have 5 minutes for questions and answers.
So I think it was in the beginning when you kind of do the factoring of the gates, you kind of commute all the polys through.
Okay. I'll try to get back, but
Yeah, so
it will take a while.
But I'm sort of like wondering, like, how do you know when you start off with your circuit that you've kind of done the best job with kind of commuting everything through?
So, you mean?
Yeah, like when you're doing this stuff.
Okay.
It's like, how do you know what the best way, the most optimal way is to kind of do this?
The best way in what sense? I mean, you can commute them all through. This will give you so the circuit that you obtain, and in principle, you can still use circuit optimization on that to reduce the T count as well as the T depth. So
yeah, I guess so. What I'm asking is like, how hard is the circuit optimization?
I don't know how hard it is, but I can show you a way, maybe a stupid way to do that. So basically, you end up with a circuit that looks like this, and you can also group your Pyruvate rotations into layers where all Pyruvate rotations mutually commute. So what you can do within a layer, you can commute Pyruvate rotations back and forth to find perhaps better layerings. So the number of layers is something like the T depth. So this is something you might minimize that way. But you can also reduce the T count because when you commute Pyruvate rotations like that, sometimes they will combine to a Pyruvate 4 rotation, which you can just throw away then. So in the paper, you'll find a greedy algorithm for that, which is not necessarily good. I don't know what the optimal way is.
Any other question?
Thanks for a great talk. So my question is, was that layout just for if you're doing one round of distillation? And if so,
yes.
Have you thought about the layout for when you do iterated
So
rounds?
So this is for this cost estimate and the way I design these protocols. This is for one round of distillation. And with one round of distillation, you can come up with protocols that are good enough, even if the output fidelity that you need is high. But for instance, here's a setup that is for 2 rounds of 15-to-1 distillation. It's not necessarily good. I think in this paper by Austin Fowler and Craig Gindley, you'll find a better one. But it's in principle something you can come up with. But then this cost metric doesn't work for that.
Yeah, the cost metric was nice. I'm just wondering, because you're doing all of the T gates sequentially, it makes it a bit more complicated if those themselves have to be distilled. Like, how do you see
exactly? Yeah.
Everything?
So it doesn't work for that. You'd have to come up with something else. Yeah.
When I look at these things, it looks like you've got a fair amount of thought required to perform a particular optimization or a particular reduction. Is there any algorithm you have for automatically doing this or for performing it in a more predictable way?
You mean to construct these protocols?
Yeah, automatically through like.
Well, I've done them all by hand, so it would be nice to have something that runs automatically. I don't know.
I could tell you did them all by hand.
Yes.
Oh, but one thing I could say, well, in principle, you can, if you have a circuit, you can straightforwardly translate it into an arrangement just by using the components that you have. So, for instance, I don't know, Earl, I broke your computer. If you have if you have an n-qubit computation, you can just use an n-qubit data block and a bunch of distillation blocks around that, and it will always work, but not necessarily work well.
In your nice talk, by the way, when you had this auto-corrected scheme for managing magic state distillation and usage earlier when you use the M states, how does that generalize when you use these phi states generally that you mentioned at the very end when you want to use something else? It's very nice for the magic states because the correction was an S, a Clifford thing.
You can do the same thing, but you'll need So for a phi rotation, you'll also need a 2 phi state and a 4 phi state and an 8 phi state, and you'll have a cascade of measurements that you do. But it works the same way. You can find a circuit in the paper for that. The time to do it may be more than just one measurement, but in the worst case, it's a bunch of measurements, but not too many. After the other, one after the other.
Okay,
Yeah.
thanks.
Let's thank Daniel once again.